I think the big difference between school mathematics and university mathematics, and the thing that people find challenging at first, is the way that they have to formulate the problem themselves, first of all. So often at school a problem is given to you. They'll say, solve this equation, integrate this function. But what makes university maths even more exciting is that someone gives you a problem, not even formulated in a mathematical way. And at university you'll learn how to write down that problem and then solve it, and that's a very, very satisfying thing. So for example, something I work on is forecasting of weather and climate. And when people make forecasts using computer models, the forecasts they make aren't necessarily precise. They're usually couched in probabilistic terms. That means that they predict a certain probability of it raining or of it not raining. And I had a student doing a project with me this year where he wanted to take these ideas that we'd developed for predicting what would happen in weather and climate and applying them to football matches. Because he spotted that when people bet on football matches, the bookies' odds are really probabilistic forecasts of what's going to happen in the football match. This student was particularly interested in Torquay United, that's his team. So we analysed all the betting history on Torquay United and how good a forecast the bookies' odds had been.
Very often we have quite a large proportion of students that don't have A-level mathematics. And in order to understand the physical processes of how radiation interacts with biological tissues, you have to have an understanding of some mathematics. So it's really, really important that people are aware that when they come into a course like radiography, they need to have a suitable background in order to come in. They can manage without A-level maths, but they have to work very hard. They can manage without A-level biology, and they may have the maths, and they have to work very hard at the biology.
One of the key problem areas that students encounter is to do with mathematical ability. I would strongly encourage all prospective physics students, science students as well, but especially physics students, to hone their skills in maths. All sorts of maths, from algebra to calculus to statistics. It all helps, and it's all an absolute requirement when dealing with some of the harder concepts in physics. So maths primarily. A kind of secondary area in which I'd really encourage students to really get motivated and to do something about their skill set is in reading, background reading. Now, it's all very well to say it's the arts, it's history, it's geography, it's everything like that requires background reading. And physics is about hard and cold facts. I wouldn't agree with that. I'd say to succeed with science, to succeed especially with physics, you need to read about all sorts of different concepts and physical areas. Again, from the large galactic cosmological type of events to the subatomic, to the nano world. A physicist at degree level for success needs to have a good breadth in their understanding and in their familiarity with physical concepts too.
There are two routes to making yourself better prepared to do physics or any science at university. I think one of them is obviously to make sure you have the academic backup. So if we're talking about physics, for example, then maths and physics are two very key requisites of doing a physics course. Further maths certainly helps, and even an AS level in further maths would certainly put you ahead of perhaps some of your colleagues on the course. But there's also a great need to be able to know more about the subject than what you've picked up in the A levels. It's nice to have a feeling of what else is going on in the world by reading the magazines like New Scientist or Science or Nature, but also to be able to develop some kind of critical analysis of what you read in the public media. So if you read an article in a newspaper, it's really useful to start thinking, you know, what parts of this article are the journalist's opinion and what is science fact, and that kind of separation of those two ideas would certainly put you in a good position to start a university course.
I mean, the key thing about science is it's built. It's famously been said that great scientists stand on the shoulders of other great scientists, or actually other scientists, and the whole process is building up knowledge from a base. And that means as an individual, you need to know the basics, and you need to know them very well, because you're going to build everything on top of them. So you need a good foundation. That means you do need to, at the lower levels of study, so this is A levels upwards through the early stage of your degree, you need to make sure you've got those fundamentals right because you're going to build on them subsequently. So quite often people see it the other way up and they think, okay, I can do this, this is easy, because it's going to get harder later, I'll concentrate later. Actually, everything's built on those lower layers. So I would say focus early. It's a difficult thing for people to do, particularly when they're going through their teenage years, but actually you focus early and get a good foundation. And that allows you to build up to these levels where it gets really interesting. So the stuff that's known, you need to know. And then you can get the stuff that's unknown to the stuff, you climb up these steps, the stuff that's unknown, then it gets interesting. Then you start to see new things. But you have to get those lower levels in place, a firm foundation.